In the vastness of time, water has journeyed endlessly across our blue planet. Each droplet carries within it an ancient story, a tale written in molecular bonds and whispered through atmospheric currents. This is the story of one such droplet, though it could be any droplet, for all water shares this eternal dance. It is a journey that has repeated itself for billions of years, long before human eyes gazed upon the seas, and will continue long after our footsteps fade from sandy shores. Our droplet's tale unfolds slowly, as all great stories do. It is a story without urgency, without haste, moving instead to the patient rhythm of Earth's own breathing, the rise and fall of temperature, the gentle pull of gravity, the quiet physics that governs every molecule on our world. The droplet rests in darkness. It has been here in the deep Pacific for longer than memory could measure. Down here, nearly 4,000 meters below the surface where sunlight never reaches, the water moves in slow, deliberate currents, rivers within the sea that flow at a pace measured in centuries rather than hours. The droplet is part of this ancient circulation, this patient conveyor belt of ocean water that connects all the world's seas. The darkness is absolute, not the darkness of a moonless night on land, where starlight still provides faint illumination, but true darkness, the complete absence of light that comes from being beneath 4 kilometers of water. No photon from the sun has penetrated to these depths in the entire history of this water mass. The only light here comes occasionally from bioluminescent creatures that drift past in the current. Jellyfish that pulse with cold chemical light, deep-sea fish with glowing lures, tiny organisms that flash when disturbed. But these are rare, and most of the time there is only darkness. The temperature here hovers just above freezing, a constant coolness that has remained unchanged for thousands of years. The water is precisely 2.3 degrees Celsius, a temperature that varies by less than 1/10 of a degree across vast distances. This stability is remarkable. While surface temperatures fluctuate with seasons and weather, rising and falling by tens of degrees, the deep ocean maintains an almost perfect constancy. The water has been this cold for millennia and will remain so for millennia more. The pressure is immense, nearly 400 times greater than at the surface. For every 10 meters of descent through the ocean, pressure increases by approximately 1 atmosphere. At 4,000 meters depth, the pressure is approximately 400 atmospheres, or about 6,000 pounds per square inch. This pressure would crush any air-filled cavity, would compress gas to a tiny fraction of its surface volume. But water is nearly incompressible, and the droplet, being liquid, is barely affected. Its volume is perhaps 1% less than it would be at the surface, a tiny compression that makes the deep water slightly denser than surface water. Yet the droplet does not notice this pressure. It simply exists, one molecule of H2O among countless trillions, bound to its neighbors by hydrogen bonds that constantly break and reform in an endless molecular dance. The droplet's 2 hydrogen atoms and single oxygen atom are arranged in that familiar bent shape, like a child's drawing of a mouse head with 2 round ears. The angle between the 2 hydrogen atoms is approximately 104.5 degrees, a consequence of the electronic structure of the oxygen atom and the repulsion between the hydrogen atoms. This geometry gives water its remarkable properties, its ability to dissolve and transport, to absorb heat, to expand when frozen. Each water molecule can form up to 4 hydrogen bonds with its neighbors. The oxygen atom can accept 2 hydrogen bonds from nearby hydrogen atoms, and each of the molecule's own hydrogen atoms can donate 1 bond to nearby oxygen atoms. In liquid water, these bonds are constantly forming and breaking, each bond lasting for only a few picoseconds before breaking and reforming with a different neighbor. This rapid shuffling creates water's fluidity, its ability to flow and conform to any container. But here in the depths, such properties seem dormant, waiting. The water is so cold and so still that the molecular motion is minimal. The hydrogen bonds last slightly longer at this temperature than they would in warm water. The dance of molecules continues, but in slow motion, a patient choreography played out over eons. Around the droplet, the ocean contains secrets. Dissolved minerals carried from distant shores exist in precise concentrations, sodium and chloride ions that give seawater its salt taste, magnesium and sulfate, calcium and potassium, and trace amounts of nearly every element on the periodic table. These ions are the product of billions of years of weathering, of rain dissolving rocks on continents and carrying the minerals to the sea, of underwater volcanoes releasing chemicals from Earth's interior, of life extracting and depositing elements in endless cycles. The salinity here is about 34.7 parts per thousand, meaning that in every kilogram of this deep water, there are 34.7 grams of dissolved salts. This is slightly less salty than surface water in the tropics, where evaporation concentrates the salt, but more salty than surface water near the poles, where melting ice dilutes the ocean. The deep water salinity reflects its origin. It was once surface water in the cold North Atlantic, water that cooled and sank centuries ago and has been flowing through the ocean's depths ever since. Microscopic particles drift in the water around the droplet. Clay particles, so fine that they take years to settle even 1 meter through the still water, having been carried from river mouths thousands of kilometers away. Particles of calcium carbonate from the dissolved shells of microscopic plankton that lived in the sunlit surface waters and died. Their remains drifting down through the water column like slow-motion snow, most dissolving before reaching this depth, but some surviving to become part of the sediment on the seafloor far below. There are particles of organic matter too, the remains of dead organisms from the surface, fragments of once living tissue now decomposed and broken down by bacteria during the long descent. These particles are rare at this depth. Most organic matter is consumed by organisms in the shallower waters. But they exist, a reminder that even this isolated deep water is connected to the sunlit world above. Cosmic dust drifts here as well. Microscopic spherules of iron and nickel that fell from space millions of years ago, vaporized during their passage through the atmosphere and then condensed into tiny metal beads that settled through the ocean to rest suspended in the deep water or accumulate in the sediment below. These extraterrestrial particles are so small, so dilute, that they are measured in parts per trillion, yet they are present evidence that the ocean accumulates not just material from Earth but from space itself. The water itself is ancient in a way that surface water is not. While surface water is constantly evaporating and being renewed by rain, constantly mixing with the atmosphere and being reoxygenated, this deep water last saw the surface perhaps 600 years ago. The oxygen dissolved in it came from contact with air during the reign of kings and emperors whose names are now only historical footnotes. That oxygen has been slowly consumed by bacteria and deep-sea organisms over the centuries, and the water is now relatively oxygen-poor compared to surface water. Though still oxygenated enough to support life, carbon dioxide is elevated in this water for the same reason. Respiration by deep-sea organisms has released CO2 over the centuries, and with no contact with the atmosphere to allow the gas to escape, the concentration has built up. This makes the deep water slightly more acidic than surface water, with a pH around 7.7 compared to the surface ocean's 8.1. This acidic water slowly dissolves calcium carbonate shells that fall from above, which is why the very deepest parts of the ocean floor are free of carbonate sediments. They dissolve before they can accumulate. The pressure at this depth affects even the chemistry of the water. Carbon dioxide becomes more soluble at high pressure, which is one reason why deep water can hold more dissolved CO2. The water's density is increased slightly by compression. Even the speed of sound is different. Sound travels faster in cold, pressurized water than in warm surface water, about 1,490 meters per second at this depth compared to 1,530 meters per second in warm tropical surface water. In this environment of cold, pressure, darkness, and stillness, the droplet exists in a state of patient equilibrium. Its molecules vibrate slowly in the cold, the hydrogen bonds that connect it to its neighbors form and break in their eternal rhythm. Time passes, but at this depth, time has little meaning. Days and nights, seasons and years, these are surface phenomena. Here, there is only the slow, steady current and the patient chemistry of cold seawater. But change comes even to these timeless depths. Far above, thousands of kilometers away and 4 kilometers straight up through the dark water, the sun warms the ocean's surface. Its radiation, having traveled 150 million kilometers across the vacuum of space, strikes the ocean and transfers energy to the water molecules there. The surface warms. Wind sweeps across tropical waters, driven by the uneven heating of Earth's atmosphere, mixing the warmed upper layers, distributing heat through the surface ocean. This surface warming is part of Earth's great heat engine. The tropics receive more solar radiation than the poles. The sun's rays strike the equatorial regions nearly perpendicular to the surface, concentrating energy, while at high latitudes the same amount of energy is spread over a larger area due to the curved surface of the Earth. This imbalance drives atmospheric circulation. Warm air rises at the equator and flows poleward, while cold polar air sinks and flows toward the equator. The same principle drives ocean circulation. Warm water at the tropical surface moves poleward, carried by surface currents. These currents are driven partly by wind, the trade winds that blow from east to west in the tropics, the westerlies that blow from west to east in mid-latitudes. The currents are deflected by the Coriolis effect, the apparent force created by Earth's rotation that causes moving objects to curve to the right in the northern hemisphere and to the left in the southern hemisphere. This deflection creates the great gyres, circular current systems that dominate each ocean basin. But surface currents are only part of the story. The ocean also circulates in 3 dimensions, with deep currents that flow beneath the surface, driven not by wind but by differences in water density. This is the thermohaline circulation, thermo for temperature and haline for salinity, the 2 properties that determine seawater density. In the cold waters near the poles, particularly in the North Atlantic and around Antarctica, surface water becomes very cold. Winter storms mix the surface layer deeply, bringing cold water down and slightly warmer water up, but the overall effect is cooling. As seawater cools, it becomes denser. And in polar regions, when sea ice forms, it excludes salt from the ice crystals, leaving the remaining water saltier. Cold and salty water is dense water. This dense water sinks. It's a slow process, not a dramatic plunge but a gradual descent over weeks and months. The water sinks until it reaches a depth where the surrounding water has the same density, and then it begins to flow horizontally, spreading across the ocean basin at that depth. This sinking water begins the deep branch of the thermohaline circulation. From the North Atlantic, dense water flows southward along the ocean floor, crosses the equator, reaches the Southern Ocean, and there joins even denser water sinking around Antarctica. This combined deep water, the coldest and densest water in the ocean, flows into the deep Indian Ocean and the deep Pacific, spreading across the seafloor of all the world's oceans. Slowly, over centuries, this deep water rises. It rises because it mixes with warmer, lighter water above it, because it is pushed upward by denser water sinking behind it, because the ocean must maintain a balance. What sinks in one place must rise in another. The rising occurs over vast areas, primarily in the Pacific and Indian Oceans, where deep water slowly wells up toward the surface. This circulation, sinking in the North Atlantic and around Antarctica, flowing through the deep ocean, rising in the Pacific and Indian Oceans, returning to the Atlantic as surface currents, takes approximately 1,000 years to complete. Water that sinks today in the Greenland Sea will not return to the surface until the year 3025. The deep Pacific contains the oldest water in the ocean, water that last saw daylight perhaps 1,600 years ago, when the Roman Empire was falling and the Dark Ages were beginning. Our droplet is caught in this grand circulation. It has been drifting in the deep Pacific for centuries already, 600 years perhaps, or 700. It was at the surface when explorers were first crossing oceans, when civilizations were rising and falling, when human history was being written. And all that time, it has been down here in the cold and dark, flowing slowly, waiting. The current that carries the droplet is part of this return flow, water that has spent centuries in the depths and is now, imperceptibly, beginning its slow journey back toward the light. The droplet begins to move, though the movement is so gradual that only instruments could detect it. The current flows at perhaps 2 centimeters per second. At this speed, the droplet travels about 1.7 kilometers per day, about 630 kilometers per year. Fast for a deep ocean current, most flow even more slowly but glacial by surface standards. Time passes in the way it does in the deep ocean, unmarked, unmeasured, patient. There are no seasons here, no day and night, nothing to mark the passage of time except the slow movement of the current. The droplet drifts northward and eastward in the deep flow, part of a river of cold water flowing beneath the warmer surface layers. Years pass, decades. The Pacific is vast, and crossing it, even with a current, takes time measured in human generations. Gradually, almost imperceptibly, the droplet begins to rise. The deep current that carries it encounters an underwater mountain range, part of the Emperor Seamount chain, ancient volcanoes that formed millions of years ago as the Pacific Plate moved over a hotspot in Earth's mantle. These seamounts rise from the abyssal plain like mountains on land, some reaching to within 1,000 meters of the surface, though they never quite break through to become islands. The current, flowing along the seafloor, cannot pass through these mountains. It must go over them. The water is forced upward, following the contours of the underwater terrain. It's a slow climb. The seamounts rise over a distance of hundreds of kilometers, and the current takes years to ascend their slopes, but it is an ascent nonetheless. The droplet rises with the flow. 3,800 meters depth. 3,500. The change is almost imperceptible, but the pressure decreases incrementally with each meter of ascent. For every 10 meters the droplet rises, the pressure decreases by about 1 atmosphere. The water expands very slightly in response to this decreased pressure, an expansion so small it's measured in parts per million, but real nonetheless. The temperature remains nearly constant during this rise. The deep ocean is isothermal, all at roughly the same cold temperature, and whether the droplet is at 4,000 meters or 3,000 meters, the water is still between 2 and 3 degrees Celsius. But the age of the water is changing. As the droplet rises, it enters water that sank more recently, water that hasn't been isolated from the surface quite as long. At 3,000 meters depth, the droplet has been rising for perhaps 20 years. It continues its slow ascent, now moving along a different current, the rising branch of a large-scale circulation cell. This upward flow is even slower than the horizontal flow, perhaps 1 meter per month, but it is persistent. The droplet rises into water that, while still deep and dark and cold, is slightly less ancient than the water below. At 2,000 meters depth, something changes. The droplet enters a different layer of the ocean, the transition between the deep water and the intermediate water above. This transition is marked not by a sharp boundary but by gradual changes in the water's properties. The temperature begins to increase, though very slowly. 2.5 degrees at 2,000 meters. 3 degrees at 1,800 meters. The salinity changes too, becoming slightly higher as the droplet enters water that originated from a different source region. The ocean, viewed from above, appears as a simple surface, a two-dimensional plane of blue water. But the ocean's interior is structured in layers, like a cake, each layer having different properties of temperature, salinity, and density. These layers are created by the way water moves through the ocean, by the locations where water sinks and rises, by the mixing processes that occur between layers. The deepest layer, the abyssal water where the droplet spent centuries, is the densest water, cold and therefore heavy, sinking to the bottom. Above this is the deep water, slightly warmer and therefore slightly lighter. Above that is intermediate water, warmer still. And at the surface is the warmest, lightest water of all. The droplet is rising through these layers, ascending from the abyssal depths toward the surface. At 1500 meters, the droplet passes through a region where oxygen concentration begins to increase. The oxygen minimum zone, a layer of water between about 400 and 1000 meters depth where oxygen is at its lowest, lies above. Below this minimum, in the deep water, oxygen is higher because the deep water was oxygenated when it last contacted the surface, even though that was centuries ago. The droplet rises toward this minimum zone. At 1000 meters depth, the droplet enters the oxygen minimum zone. Here, oxygen has been depleted by respiration, fish and bacteria and other organisms consuming oxygen, but is not replenished because this water has been isolated from the surface for a long time, though not as long as the deep water below. The oxygen concentration is low enough that only specially adapted organisms can survive here. Most fish avoid this layer, but it's not devoid of life. There are creatures adapted to low oxygen and bacteria that can use other chemical pathways for energy. The droplet continues to rise. 900 meters. 800. The oxygen concentration reaches its minimum, barely 2 milliliters of oxygen per liter of water, compared to 6 or 7 milliliters near the surface. Then, as the droplet rises further, the oxygen begins to increase again. At 700 meters, it's slightly higher. At 600, higher still. The droplet is approaching the thermocline, the layer of ocean where temperature changes rapidly with depth. In the deep ocean below, temperature changed very little over vast vertical distances. But in the thermocline, temperature increases dramatically as the droplet approaches the sun-warmed surface layers. At 500 meters depth, the temperature is about 8 degrees Celsius, cold still, but noticeably warmer than the deep water below. At 400 meters, 10 degrees. The droplet is rising through water that is not only lighter but visibly different. Even in this depth, where almost no light penetrates, there is the faintest hint of illumination from above. Not enough to see by, but enough to register on sensitive instruments as something other than absolute darkness. At 300 meters, the temperature reaches 12 degrees. The droplet is in the twilight zone now, the layer of ocean where sunlight penetrates but is too dim for photosynthesis. This is a realm of strange fish with huge eyes adapted to see in near darkness, of bioluminescent organisms that create their own light, of migrating creatures that rise to feed at the surface at night and descend to these depths during the day to hide from predators. The rise continues. 200 meters. 150. The light is stronger now, though still dim. A deep blue twilight. The temperature continues to increase. 15 degrees at 200 meters. The droplet is leaving the thermocline and entering the mixed layer, the upper 100 meters of ocean where wind and waves stir the water, creating a relatively uniform temperature and salinity from the surface down to about 100 meters depth. The hydrogen bonds that connect the droplet to its neighboring molecules continue their constant breaking and reforming. Each bond exists for only a tiny fraction of a second before it breaks and a new bond forms with a different neighbor. This endless reshuffling means that the droplet is not really a fixed collection of molecules at all, but rather a concept, a particular region of space that contains water molecules, even as those specific molecules constantly change. At 100 meters depth, the water is noticeably warmer. The droplet has entered the ocean's mixed layer, where wave action and wind-driven turbulence stir the water, creating a relatively uniform temperature from the surface down to a depth of about 100 meters. Here, the temperature is perhaps 15 degrees Celsius, still cool, but warmed by the sun that shines on the surface above. The droplet continues to rise, carried by complex currents and eddies within this mixed layer. It spirals slowly upward in turbulent flows too gentle to be called violent, too persistent to be called random. The physics of fluid dynamics governs every movement. Invisible forces of pressure and momentum, of friction and inertia, all balanced in the intricate choreography of moving water. Days pass, weeks. The droplet wanders through the upper ocean, sometimes rising, sometimes sinking slightly, but overall trending upward toward the light. And then, one quiet morning, it reaches the surface. The transition is unremarkable. One moment the droplet is part of the water column, surrounded on all sides by ocean. The next moment it finds itself at the boundary between water and air, part of the thin surface film that separates two worlds. Above, the sky stretches vast and blue. The sun climbs slowly toward its zenith. The droplet sits at the surface, part of a gently rolling swell moving across the tropical Pacific. Here, the water temperature is warmer still, perhaps 28 degrees Celsius, heated by the intense tropical sun. The sun's radiation pours down from a sky that is deep blue and nearly cloudless. This radiation carries energy from the nuclear fusion reactions occurring in the solar core 93 million miles away, hydrogen atoms fusing into helium in the sun's core, releasing energy according to Einstein's famous equation E=mc², energy that radiates outward and takes about 8 minutes to cross the distance from sun to Earth. This solar radiation, transmitted across the vacuum of space as electromagnetic radiation, strikes the ocean surface and is absorbed by the water molecules. Most of the energy comes in the visible and near-infrared wavelengths, the spectrum of light that warms rather than burns. The water absorbs this radiation, and the energy is converted to molecular motion. The water molecules vibrate more vigorously, rotating and translating more energetically. The droplet absorbs this energy. Its molecules, which were already in constant thermal motion, begin to move even more rapidly. At 28 degrees Celsius, the average kinetic energy of a water molecule is about 4.3 times 10 superscript 2 superscript 1 joules, a tiny amount of energy for each individual molecule, but multiplied by the trillions of molecules in even a small volume of water, it represents substantial heat. This thermal energy manifests as motion. The water molecules are not still but constantly vibrating, rotating, and translating. They vibrate with their bonds stretching and compressing hundreds of trillions of times per second. They rotate, spinning end over end in chaotic tumbling motions. And they translate, moving through space, constantly colliding with their neighbors in a ceaseless molecular ballet. The hydrogen bonds that connect the droplet to its neighbors weaken slightly as the thermal energy increases molecular motion. Each hydrogen bond has a certain strength, about 20 kilojoules per mole, which sounds like a lot but is actually weak compared to the covalent bonds that hold each water molecule together. The oxygen-hydrogen bonds within a molecule are about 460 kilojoules per mole, more than 20 times stronger. These weak hydrogen bonds can be broken by thermal energy, and at higher temperatures they break more frequently. But the droplet does not evaporate immediately. Evaporation is not a simple matter of temperature. If it were, all water at room temperature would evaporate instantly, which clearly doesn't happen. Instead, evaporation is a statistical process, dependent on the energy distribution among molecules and the constant competition between molecules that have enough energy to escape and the attractive forces that hold them in the liquid. The droplet sits at the surface, warmed by the sun, for hours. The tropical day progresses. The sun, which rose from the eastern horizon at dawn, climbs slowly toward its zenith. The angle of the sun's rays changes, and with it the intensity of radiation hitting each square meter of ocean surface. At dawn and dusk, sunlight strikes at a shallow angle and much of it is reflected. But as the sun rises higher, more radiation penetrates the surface and is absorbed. A light wind blows across the ocean, driven by the temperature difference between the warm ocean and the slightly cooler air above. This wind is part of the trade wind system, the steady easterly winds that blow across tropical oceans, driven by the general circulation of Earth's atmosphere. The wind creates ripples on the ocean surface. Small waves rise and fall, their size determined by wind speed and the distance over which the wind has been blowing, the fetch, as sailors call it. The droplet rides up the gentle slope of a swell, then down into a shallow trough. These swells were generated by storms thousands of kilometers away, low-pressure systems in the mid-latitudes where strong winds created large waves that have propagated across the ocean as swell, organized patterns of waves that travel vast distances from their source. The droplet is tossed by these small movements, never far from the surface, part of the thin film of water that forms the ocean atmosphere interface. This interface is crucial to evaporation. It's here, in the topmost millimeter of the ocean, that water molecules can escape into the atmosphere. Molecules deeper in the water column are held by hydrogen bonds on all sides and cannot escape. But molecules at the surface have hydrogen bonds only pulling them downward and sideways. Above them is air, not more water. The sun climbs higher. The heat increases. More energy flows into the water. The surface temperature rises slightly, perhaps from 27.8 degrees to 28.3 degrees over the course of the morning. This small increase represents a significant amount of energy. Water has a high heat capacity, meaning it takes a lot of energy to raise its temperature, which is one reason why oceans moderate Earth's climate, absorbing heat in summer and releasing it in winter. And then, in a moment that seems both sudden and inevitable, it happens. The thermal vibrations of the droplet's molecules become strong enough to overcome the hydrogen bonds holding them to their neighbors. This doesn't happen all at once to all molecules. It happens molecule by molecule, each molecule having a slightly different energy at any given instant due to random collisions with neighbors. The droplet contains perhaps 10 superscript 2 molecules, 10 billion trillion individual water molecules, each with its own instantaneous velocity and kinetic energy. These energies follow a distribution. Most molecules have energy close to the average, but some have more and some have less. This is called the Maxwell-Boltzmann distribution, and it describes how energy is spread among molecules in any substance at a given temperature. At any instant, a small fraction of the molecules, perhaps 1 in a million, have enough energy to overcome the hydrogen bonds holding them in the liquid. These high-energy molecules, if they happen to be at the surface, can escape into the air. This is evaporation, the constant escape of the most energetic molecules from the liquid surface. The thermal vibrations reach a critical point. For one particular molecule at the surface, one of the molecules that was part of our droplet's original collection, the random collisions with its neighbors have given it unusually high kinetic energy. Its velocity is much higher than average. It's moving upward, toward the air above. The molecule approaches the surface. The hydrogen bonds to molecules below it stretch. The oxygen atom in one neighbor molecule, to which our molecule's hydrogen atom is bonded, pulls back, but the bond stretches and weakens. Another hydrogen bond, connecting our molecule's oxygen to a hydrogen in another neighbor, also stretches. The thermal kinetic energy of the molecule is greater than the binding energy of these hydrogen bonds. The bonds break, not all at once but one by one. First, one hydrogen bond snaps, freeing one side of the molecule. Then another breaks, and another. Each breaking bond releases the molecule a little more from the collective embrace of the liquid. The droplet's oxygen atom, pulled by its random thermal motion and no longer held firmly by hydrogen bonds, breaks its last connection to the liquid water below. The molecule passes through the surface interface and enters the air above. In an instant, a time measured in picoseconds, the droplet transitions from liquid to gas. This particular molecule has become water vapor. But our droplet consists of trillions of molecules. One molecule evaporating doesn't change that. The evaporation continues, molecule after molecule. Over the course of perhaps 10 seconds, all the molecules that we've been thinking of as the droplet, those that have traveled together from the deep ocean, have gained enough energy and have found themselves at the surface at the right moment to evaporate. The transformation is complete in seconds, yet it represents a fundamental change in state. As a liquid, the droplet's molecules were held close together by hydrogen bonds, able to flow but confined to a specific volume, separated from each other by only about 3 angstroms, 3/10,000,000,000ths of a meter. Their motion was constrained. They could vibrate and rotate and slide past each other, but they were always in contact with neighbors, always held in the collective grip of the liquid. As vapor, those bonds are broken. The molecules are free, bouncing through space as an invisible gas, no longer touching their neighbors except in brief, elastic collisions. Each molecule now occupies vastly more space. In the liquid, the molecules were packed tightly together. As vapor, at the same temperature, the average distance between molecules is about 30 angstroms, 10 times farther apart. And because volume scales with the cube of distance, this means each molecule occupies about 1,000 times more space as vapor than it did as liquid. Water vapor is indeed invisible. Unlike the visible white clouds that form when vapor condenses into tiny liquid droplets, pure water vapor is as invisible as the nitrogen and oxygen that make up most of the atmosphere. The molecules are so far apart, so spread out, that they don't interact with visible light. Light passes through the vapor without scattering, without absorption, as if nothing were there. The newly vaporized molecules, what we might still call our droplet, though it is no longer drop-shaped or even confined to a drop-sized region of space, immediately begin to move upward. Water vapor, with a molecular weight of 18 grams per mole, is significantly lighter than dry air, which has an average molecular weight of about 29 grams per mole, nitrogen at 28, oxygen at 32, weighted by their proportions in air. This difference in molecular weight means that humid air is less dense than dry air at the same temperature and pressure, contrary to common intuition. The water vapor, being lighter, tends to rise. But it's not just buoyancy that moves the vapor upward. The wind at the surface creates turbulence, chaotic eddies and swirls in the air, mixing on scales from millimeters to meters. This turbulence rapidly disperses the evaporated molecules, mixing them with the surrounding air. Within minutes of evaporating, our droplets' molecules have been dispersed through a volume of air perhaps a meter in diameter, mixed with billions of trillions of molecules of nitrogen, oxygen, argon, and carbon dioxide that make up the atmosphere. The droplet ascends through air that is warm and humid. This region above the tropical ocean is one of Earth's great evaporating zones, where the sun's heat lifts vast quantities of water into the atmosphere every day. The global evaporation rate from oceans is about 1,250 cubic kilometers of water per day, enough to cover the entire ocean surface with a layer about 3 millimeters thick. Our droplet is part of this invisible river flowing upward, a stream of water vapor rising from sea to sky. As the droplet climbs, it spreads out. The molecules that were once bound together in a compact droplet are now scattered through a much larger volume of air, each molecule bouncing independently, separated from its former neighbors by distances thousands of times greater than when they were liquid. The average molecule of water vapor at sea level moves at about 650 meters per second, nearly twice the speed of sound, though this rapid molecular motion is random in all directions, so the net movement is much slower. The vapor molecules collide with air molecules billions of times per second, changing direction with each collision, following a random walk through the atmosphere. Yet we can still follow this dispersed collection of molecules, this ghost of the droplet that once was. Though scattered, the molecules rise together, part of the same parcel of warm, moist air ascending from the ocean surface. Meteorologists speak of air parcels, imaginary bubbles of air that can be tracked as they move through the atmosphere. Even though the molecules constantly mix with surrounding air, our droplets molecules are part of such a parcel, a column of humid air perhaps 100 meters in diameter, rising from the warm ocean surface. The ascent is steady but not rapid. The air rises at perhaps 1 to 2 meters per second, faster than the deep ocean currents, but slow compared to winds and storms. This is convective rising, driven by buoyancy. The warm, humid air at the ocean surface is less dense than the cooler air above, and so it rises just as a hot air balloon rises through the cooler surrounding atmosphere. The droplets' constituent molecules climb through the lower atmosphere, the boundary layer where ocean and sky exchange heat and moisture. This boundary layer, typically about 1 or 2 kilometers thick, is where the atmosphere directly feels the influence of the surface below. Within this layer, the air's temperature and humidity are strongly affected by the ocean. Above this layer, in the free atmosphere, the air's properties are determined more by large-scale atmospheric circulation than by the local surface. As the air rises, it begins to cool. This cooling is not because the air is moving away from the sun. It's barely a kilometer or two higher, and the sun is 150 million kilometers away, so this tiny change in distance is irrelevant. Instead, the cooling is the result of decreasing atmospheric pressure. Atmospheric pressure decreases with altitude because there is less air above pressing down. At sea level, the weight of the entire atmosphere above creates a pressure of about 101,325 pascals, or 1,013 millibars. For every kilometer of altitude, the pressure decreases by roughly 12%, following a logarithmic decay. This means that at 1 kilometer altitude, the pressure is about 900 millibars, at 2 kilometers about 800 millibars, at 5 kilometers about 550 millibars. As the parcel of air rises into regions of lower pressure, it expands. The air molecules, no longer compressed as tightly by the weight of air above, spread out to fill more space. This expansion requires energy. Work must be done to push aside the surrounding air as the parcel expands. That energy comes from the parcel's own internal heat. As the air expands, it does work on its surroundings, and this work comes at the expense of the air's thermal energy. The air cools. This cooling follows a predictable pattern described by the dry adiabatic lapse rate, the rate at which temperature decreases with altitude for air that is rising without condensation occurring. The rate is about 9.8 degrees Celsius for every 1,000 meters of altitude, a value determined by the physics of gas expansion and the specific heat capacity of air. The warm air that left the ocean surface at 28 degrees Celsius becomes cooler as it climbs. At 200 meters altitude, the temperature has dropped to about 26 degrees. At 400 meters, about 24 degrees. The invisible water vapor molecules cool along with the air, their kinetic energy decreasing, their random thermal vibrations slowing slightly. The droplets molecules continue to rise, mixed with nitrogen, oxygen, and the other gases that make up Earth's atmosphere. They pass through air that is moving in complex patterns, trade winds blowing westward across the tropical Pacific, localized circulations driven by uneven heating, turbulent eddies on scales from millimeters to kilometers. At 1,000 meters altitude, the air temperature has dropped to 18 degrees Celsius. The water vapor is still invisible, still a gas, but it is approaching a critical threshold. Air can hold only a certain amount of water vapor at any given temperature, and this capacity decreases as temperature falls. The rising continues. 1,500 meters, 2,000. The air cools to 12 degrees, then 10. The relative humidity of the air parcel increases as the temperature drops, even though the actual amount of water vapor remains constant. Cool air can hold less moisture than warm air, and so the air becomes increasingly saturated. At about 3,000 meters altitude, something fundamental changes. The air temperature has fallen to approximately 6 degrees Celsius. The pressure is about 700 millibars, roughly 70% of sea level pressure. The droplets' water vapor molecules are still invisible, still individual molecules bouncing randomly through the air. But the air has cooled to the point where it can no longer hold as much water vapor. At this temperature, at this altitude, at this level of moisture, the air reaches its dew point, the temperature at which it becomes saturated with water vapor. The concept of saturation is crucial to understanding clouds. Air at any given temperature can hold only a certain maximum amount of water vapor before that vapor begins to condense. Warmer air can hold more vapor than cooler air. This is why warm tropical air feels humid while cold polar air feels dry. The relationship is exponential. Air at 30 degrees Celsius can hold about 4 times as much water vapor as air at 10 degrees Celsius. As rising air cools, its capacity to hold water vapor decreases. The actual amount of vapor in the air doesn't change, the same number of water molecules are present, but the saturation vapor pressure decreases with temperature. Eventually, the air cools enough that its water vapor content equals the maximum it can hold. The relative humidity reaches 100%. The air is saturated. At saturation, a delicate balance exists. Water molecules are constantly evaporating from any tiny liquid water droplets that might be present, and water vapor molecules are constantly condensing onto those droplets. At saturation, these two rates are equal. Below saturation, evaporation dominates and droplets shrink. Above saturation, condensation dominates and droplets grow. The rising air has now cooled below its dew point. It is technically supersaturated. The relative humidity is slightly above 100%, perhaps 100.5% or 101%. In this supersaturated condition, water vapor should condense. But there's a problem. The water vapor can remain gaseous even when supersaturated, reluctant to condense on its own. This is because forming a new droplet from pure vapor requires overcoming surface tension. A very small droplet has an extremely curved surface, and this curvature creates additional pressure inside the droplet that opposes condensation. For a droplet to form spontaneously from pure vapor would require extreme supersaturation, perhaps 300% or 400% relative humidity, which virtually never occurs in Earth's atmosphere. Pure water vapor, even in supersaturated air, is reluctant to condense spontaneously. Water molecules need something to condense onto, a surface that can serve as a nucleation site, a place where the physics favors condensation. Fortunately, the atmosphere is full of such surfaces. Tiny particles drift through the air at this altitude, aerosols, as they're called by atmospheric scientists. These particles come from many sources. There are microscopic grains of dust blown from distant deserts, perhaps from the Sahara or the Gobi, lofted into the atmosphere by strong winds and carried thousands of kilometers by atmospheric circulation. Each grain is smaller than a red blood cell, often just 1 or 2 microns across, but large enough to serve as a condensation nucleus. There are salt crystals too, ejected from sea spray when waves break and bubbles burst at the ocean surface. As the spray evaporates, it leaves behind tiny crystals of sodium chloride and other sea salts, particles that are particularly effective as condensation nuclei because they are hygroscopic, water-attracting. A salt particle will start to accumulate water even before the air reaches 100% relative humidity. Other aerosols include specks of pollen carried up from forests below, though most pollen is too heavy to reach this altitude. There are particles from volcanic eruptions, sulfate aerosols formed when sulfur dioxide from volcanoes reacts with water in the atmosphere. There are even particles from space, meteoric dust that burns up in the upper atmosphere and settles slowly through the stratosphere and into the troposphere. And increasingly, there are particles from human activities, soot from combustion, sulfate particles from industrial emissions. The concentration of these aerosols varies greatly depending on location. Over the open ocean, far from land, aerosol concentrations might be just a few hundred particles per cubic centimeter. Over continental regions or near sources of pollution, concentrations can be thousands or tens of thousands per cubic centimeter. Here, at 3,000 meters above the mid-Pacific, the concentration is moderate, perhaps 1,000 particles per cubic centimeter, mostly sea salt with some dust. As the rising air reaches saturation and then slight supersaturation, these aerosol particles become active. Water vapor molecules, in their constant random motion, strike the surfaces of these particles. And when they do, many of them stick. One of the droplet's molecules, one particular H2O molecule that was part of the original droplet in the deep ocean, that evaporated from the tropical surface, that has risen 3,000 meters as invisible vapor, encounters a speck of dust. The dust particle is perhaps half a micron across, roughly spherical, a fragment of clay from a desert thousands of miles away. The particle was lofted into the atmosphere by a dust storm weeks ago, carried by winds across the Pacific, and now drifts at this altitude, waiting. The water molecule, moving in its random thermal motion at about 650 meters per second, strikes the surface of this dust particle. The particle's surface at the molecular scale is not smooth but irregular, with peaks and valleys corresponding to the atomic structure of the clay mineral. The water molecule's oxygen atom approaches the surface. Electrons in the oxygen atom interact with electrons in the surface atoms of the clay. A weak attraction develops, a hydrogen bond between the water molecule and atoms on the mineral surface. The molecule sticks. It has condensed from vapor back to liquid, the first liquid water molecule on this particular dust particle. The energy the molecule had as vapor, its kinetic energy of motion plus the latent heat of vaporization, is released when it condenses. About 2,260 joules of energy per gram of water is released during condensation, the same amount of energy that was required to evaporate it from the ocean surface. This energy is transferred to the surrounding air and to the dust particle, warming them very slightly. For a single molecule, this is an imperceptible amount of heat, but when billions of droplets are forming simultaneously, the latent heat release can significantly warm the air parcel, which is why clouds often create their own updrafts. Within moments, other water molecules join the first one. They too strike the dust particle and stick, adding to the growing collection of liquid water. One molecule becomes 10, becomes 100, becomes thousands, becomes millions. Each arriving molecule forms hydrogen bonds with the molecules already present, building up a film of liquid water around the solid nucleus. The growth is rapid at first. In supersaturated air, condensation dominates, and vapor molecules stick to the liquid surface faster than they evaporate. Within seconds, there are billions of water molecules coating the dust particle. The water layer is several molecules thick. A microscopic droplet has formed, a sphere of liquid water surrounding the dust nucleus, held together by surface tension and hydrogen bonds. The droplet grows to perhaps 10 microns in diameter, about 1/100th of a millimeter, far smaller than the width of a human hair, but large enough to be visible under a microscope, large enough to begin behaving like a proper liquid droplet rather than just a few molecules clinging to a dust grain. All around, the same process is occurring. Billions upon billions of water molecules are condensing onto billions of aerosol particles. An invisible parcel of humid air transforms into a visible cloud. The cloud begins to form at the exact altitude where the air reaches its dew point. Below this level, the air remains clear, the water vapor is still invisible gas. At and above this level, water vapor condenses into microscopic droplets, and the air becomes opaque, white with scattered sunlight. This boundary, sharp when seen from a distance, is the cloud base. Our droplet, now reformed as a tiny cloud droplet, merged with others around a dust nucleus, drifts in this newborn cloud. The cloud is a cumulus, a puffy fairweather cloud forming over the ocean. It grows as more humid air rises from below, bringing more water vapor to condense at the cloud base. The cloud billows upward, white and bright in the afternoon sun. Inside the cloud, the tiny droplet floats in a world of mist. Billions of other cloud droplets surround it, each separated from its neighbors by distances hundreds of times their own diameter. Light scatters from these countless tiny droplets, bouncing in all directions, making the cloud appear brilliant white from outside, while the interior is filled with a soft, diffuse glow. The droplet is now airborne as a cloud droplet, roughly 10 microns in diameter. At this size, it is genuinely tiny. There could be 100 such droplets side by side across the width of a human hair. The droplet is so small that air resistance completely dominates its motion. Its terminal velocity, the speed at which gravitational force downward equals air resistance upward, is approximately 1 centimeter per hour. For practical purposes, it is not falling at all, but floating, suspended in the air. All around, the same process is occurring simultaneously on billions upon billions of aerosol particles. An invisible parcel of humid air, supersaturated and cooling, transforms into a visible cloud as water vapor condenses onto aerosols throughout the air mass. The transformation happens at the exact altitude where the air reaches its dew point. Below this level, the air remains clear, the water vapor is still invisible gas, and if you could fly through it, you would see nothing but blue sky. At and above this level, water vapor condenses into microscopic droplets, and the air becomes opaque, white with scattered sunlight. This boundary, sharp when seen from a distance, is the cloud base. Our droplet, now reformed as a tiny cloud droplet, merged with other water molecules around a dust nucleus, drifts in this newborn cloud. The cloud is a cumulus, a puffy fairweather cloud forming over the ocean. It grows as more humid air rises from below, bringing more water vapor to condense at the cloud base. The cloud billows upward, white and bright in the afternoon sun, its top pushing higher and higher into the sky as the updraft continues. Inside the cloud, the tiny droplet floats in a world of mist. Billions of other cloud droplets surround it, filling the air, though they are not packed densely. Each droplet is separated from its nearest neighbors by distances hundreds of times their own diameter. If the droplets were marbles, and they maintained the same spacing they have in a cloud, you could walk between them without touching any. But because there are so many, typically 1 billion droplets per cubic meter in a cloud, they collectively make the air opaque. Light scatters from these countless tiny droplets, bouncing in all directions through the cloud. This scattering is why clouds appear white. All wavelengths of visible light are scattered equally by the small droplets, and white light scattered in all directions appears white. The interior of the cloud is filled with a soft, diffuse glow, light bouncing between droplets thousands of times before finally emerging from the cloud surface or being absorbed. The droplet is far too small to fall. A 10-micron droplet falling through air experiences drag force that is proportional to its velocity, Stokes drag, applicable to very small particles. The gravitational force is proportional to the droplet's volume, and therefore to the cube of its radius. For a very small droplet, the drag force overwhelms gravity, and the terminal velocity becomes imperceptibly small. The droplet is effectively weightless, drifting with the air currents inside the cloud. The cloud continues to build vertically. Air rises through the cloud's core at perhaps 2 to 3 meters per second, carrying more moisture upward, feeding the cloud's growth. The cloud grows taller, reaching 4,000 meters, then 5,000, its top cooling as it rises, its base remaining near 3,000 meters where the dew point level lies. Our droplet is carried upward with this flow, rising through the cloud's interior in the gentle updraft. As it rises with the air, it continues to exist in supersaturated conditions. The air is constantly cooling as it rises, constantly creating conditions favorable for continued condensation. and so the droplet begins to grow. Cloud droplets grow through two main processes. The first is continued condensation. As the air around the droplet remains supersaturated, more water vapor molecules strike the droplet's surface and stick, adding to its mass molecule by molecule. This process is called diffusional growth because water vapor diffuses through the air toward the droplet's surface. The growth rate from diffusion depends on how supersaturated the air is. At 101% relative humidity, 1% supersaturation, a droplet might grow at perhaps 0.1 microns per minute. This sounds fast, but remember the droplet is starting at 10 microns diameter. To grow from 10 microns to 20 microns would take about 100 minutes, nearly 2 hours at this growth rate. The second growth process is collision and coalescence. The droplet, as it drifts through the cloud, occasionally encounters other droplets. Cloud droplets are constantly moving relative to each other, carried by turbulent eddies in the air, some rising slightly faster than others in updrafts, some drifting sideways. Eventually, two droplets come close enough that they touch. When two droplets collide, several things can happen. They might bounce apart if the collision is too energetic, or if a thin film of air gets trapped between them. But often they merge, combining into a single larger droplet. This process is called coalescence. Surface tension pulls the two droplets together into one spherical drop, and the coalescence is complete in milliseconds. Our droplet grows slowly through both processes. Diffusional condensation adds water vapor continuously, molecule by molecule. Every few minutes, perhaps, it collides with another small droplet and they merge. 10 microns becomes 12. 12 becomes 15. 15 becomes 20. The growth is exponential in a sense. Larger droplets have more surface area and therefore collect vapor faster, and they also sweep out a larger volume of air as they move, encountering more small droplets to absorb. But it's still slow. Hours pass inside the cloud. The cloud begins to age. The strong updrafts weaken. The supply of humid air from below diminishes. The cloud has reached a quasi-steady state, no longer growing vigorously but not yet dissipating. Inside this mature cloud, the droplet has grown to perhaps 50 microns, large for a cloud droplet, though still small compared to raindrops. At this size, its terminal velocity is about 30 centimeters per second. It begins to fall slowly relative to the air, though the air's own motions still dominate its path. As it falls, it continues to collide with smaller droplets that remain suspended. With each collision and merger, it grows. 60 microns, 80, 100. The growth accelerates. Larger droplets fall faster and therefore sweep out a larger volume of air, encountering more small droplets to absorb. This is the beginning of precipitation. The droplet has grown large enough that we might call it a drizzle drop. Still small, but falling with purpose now, descending through the cloud at about a meter per second. It collides with many smaller droplets in its path, growing steadily. 150 microns, 200. But this particular cloud is not destined to produce rain today. The updrafts, though weak, are still strong enough to keep most drops from falling out of the cloud base. The droplet circulates within the cloud, rising and falling, growing and occasionally breaking apart in turbulent eddies, for another hour. Then the cloud begins to dissipate. The sun, now past its zenith and beginning its descent toward the western horizon, no longer heats the ocean surface as intensely. The supply of warm, humid air from below ceases. The cloud's droplets begin to evaporate as drier air mixes in from the sides. Our droplet, now about 100 microns across, begins to evaporate too. Its surface molecules gain enough energy to break free and return to vapor. The droplet shrinks. The process that formed it reverses. Within minutes, it has evaporated completely, returning once more to invisible water vapor. But this is not a return to the beginning. The droplets' molecules are now at 5,000 meters altitude, far above the ocean where they began this chapter of their journey. They drift in the upper troposphere, carried by winds that blow at this altitude. Days pass. The water vapor molecules drift eastward with the prevailing winds, part of the vast atmospheric circulation that transports heat and moisture around the globe. They cross the Pacific, moving from the tropics toward the mid-latitudes. The air mass containing them gradually changes. Tropical air gives way to subtropical, then temperate. The vapor molecules mix with drier air from continental regions. They rise and sink with large-scale atmospheric motions, sometimes condensing into clouds, sometimes evaporating again, always moving eastward. Weeks pass in this atmospheric wandering. The molecules drift across the ocean, thousands of kilometers from where they first evaporated. The air mass cools gradually as it moves into higher latitudes. Then, off the coast of a distant continent, the air mass encounters a weather system, a mid-latitude cyclone, a great spiral of wind and cloud spinning around a low-pressure center. The vapor molecules are drawn into the system, caught in the counterclockwise circulation of the storm. They rise rapidly now, pulled upward in the strong updrafts near the storm's center. The air cools quickly as it rises, 5 degrees per kilometer, 8 degrees, 10. At 6,000 meters altitude, the temperature has fallen below freezing. The water vapor around our droplets molecules should condense, should freeze, but the air is rising so fast that it becomes supersaturated, holding more vapor than it should be able to contain. Then, at 7,000 meters, condensation finally occurs. The molecules encounter ice crystals that have formed higher in the cloud, tiny hexagonal crystals of frozen water. The supercooled vapor deposits directly onto these ice crystals, bypassing the liquid phase entirely, transforming from gas to solid in a process called deposition. Our droplets molecules are separated now. Some deposit onto one ice crystal, others onto different crystals nearby. But we can follow one particular crystal that has captured several of the molecules that travel together from the deep Pacific. The ice crystal grows rapidly. In the cold upper reaches of the storm cloud, water vapor is abundant and supersaturated. The crystal's hexagonal structure provides perfect sites for vapor molecules to attach, and they do so eagerly, building up the crystal's intricate six-fold symmetry. The crystal develops branches, becoming a dendritic snowflake, a stellar crystal with 6 elaborate arms radiating from a central core. Each arm grows in the same pattern, because each faces identical conditions of temperature and humidity, and ice crystals grow in ways that reflect their molecular structure. The familiar 6-sided symmetry of snowflakes emerges from the 6-fold symmetry of water molecules arranged in ice's crystalline lattice. The growing snowflake is beautiful, though there is no one to see it here in the heart of the storm cloud. It tumbles slowly as it grows, ensuring that each arm experiences similar conditions. The temperature is about -15 degrees Celsius, cold enough for rapid growth, warm enough that the crystal takes the stellar dendritic form rather than the simple plates or columns that form at other temperatures. The snowflake grows to a few millimeters across, large enough to begin falling through the cloud. It descends through regions of different temperature and humidity, and its form records this journey. The 6 arms show subtle variations in their branching patterns, a history written in ice of the snowflake's path through the cloud. At 4,000 meters, the snowflake passes below the freezing level. The air temperature is now above 0 degrees Celsius. The ice begins to melt. The intricate crystal structure, so carefully built over the course of an hour, begins to dissolve. Water forms on the crystal's surface, the ice melting from outside in. The snowflake transitions back to liquid water. It becomes a raindrop. The drop is large, several millimeters across, because it formed from a sizable snowflake. Its shape is not the teardrop often depicted in cartoons, but rather a flattened sphere, slightly squashed by air resistance as it falls. Surface tension holds it together, creating a thin skin of higher density water that contains the drop's interior. Inside this raindrop are the molecules we have been following, a tiny fraction of the drop's total mass, mixed with millions of other molecules from the melted snowflake. The drop falls through the cloud, growing slightly as it collides with smaller droplets, but mostly just descending. It falls at about 8 meters per second, pulled downward by gravity, its speed limited by air resistance. It passes through the cloud base at 2,000 meters altitude and enters clear air below the cloud. The storm's rain curtain is visible from a distance, a gray veil hanging beneath the clouds, a visible manifestation of countless falling drops. The raindrop falls through cooling air. Below, the land is approaching. This is not the tropical ocean where the water originally evaporated, but a coastal mountain range thousands of kilometers away. Green peaks rise to meet the falling rain, their slopes covered in temperate forest. At 1,000 meters above the surface, the drop falls through air that is thick with the scent of wet earth, petrichor, that distinctive smell of rain on soil, caused by oils released from plants and bacteria disturbed by the falling drops. The raindrop is approaching the ground. 500 meters altitude. 300. The mountain slope rises to meet it, clad in fir and spruce, the trees bending in the storm's wind. 100 meters. 50. And then, gently, inevitably, the raindrop strikes the surface. It lands on a granite boulder near a mountain peak, one of many drops pattering onto the stone surface. The impact spreads the drop across a small area of rock, and for a moment it sits there, a thin film of water on cold gray granite. But the rock is tilted, part of a steep mountain slope, and gravity pulls at the water. The film begins to flow, drawn downward by the slightest gradient. It joins other drops that have fallen nearby, and together they form a rivulet, a tiny stream of water trickling down the boulder's surface. Our droplet, or rather, the molecules we have been following, now mixed with many others in this rivulet, flows down the granite. The water follows microscopic channels and cracks in the rock, finding the path of least resistance downward. The rivulet reaches the edge of the boulder and drips off, falling a few centimeters to land in moss growing in the cracks between rocks. The moss absorbs some water, but most flows through it, seeping downward into the spaces between pebbles and stones. The water percolates into the ground, entering the mountain soil. This seepage is slow, not a rapid plunge but a gradual infiltration. The soil here is not deeply developed. Mountain soils are young, constantly refreshed by erosion and weathering. There is a thin layer of organic-rich topsoil, perhaps 20 centimeters deep, dark brown with decomposed plant matter, roots, and soil organisms. Beneath this is mineral soil, lighter in color, derived from the weathering of the granite bedrock below. The soil is not saturated. This storm is the first significant rain after a dry spell lasting several weeks, and the ground is thirsty. The soil particles, clay, silt, and sand grains, have been dry, and now water fills the tiny spaces between them. Water first coats each particle with a thin film, adhering to the particle surface through adhesive forces. Then, as more water arrives, it begins to fill the pores, the spaces between particles, through cohesive forces between water molecules. The movement of water through soil is governed by several forces. Gravity pulls water downward, but capillary action can pull it in other directions, even upward, through narrow pores. The balance between these forces determines how water moves. In saturated soil, gravity dominates and water flows downward. In unsaturated soil, capillary forces compete with gravity, and water can move sideways or even upward toward roots that are actively absorbing it. As water percolates downward, some is absorbed by plant roots. The forest above, Douglas fir, western hemlock, salal shrubs, sword ferns, drinks deeply. Roots extend throughout the soil profile, some reaching depths of several meters. The roots absorb water through osmosis. Water moves from the soil, where the concentration of dissolved minerals is low, into root cells, where the concentration is higher. This water is transported up through the plant's xylem, tubular cells that form continuous columns from root to leaf, pulled upward by the evaporation of water from leaf surfaces. A process called transpiration. Our droplets molecules could easily have been absorbed by a root, could have become part of a tree, could have been transpired from leaves back into the atmosphere. But they avoid the roots, perhaps by chance, perhaps because they percolate through a region where root density is low. Instead, they seep deeper into the soil profile. The water moves slowly, following gravity but impeded by the tortuous path through soil pores. The percolation rate is perhaps a few centimeters per day, depending on the soil's hydraulic conductivity, its ability to transmit water. Sandy soils with large pores conduct water quickly. Clay soils with tiny pores conduct water very slowly. This soil, derived from granite, is somewhere between a mixture of particle sizes creating moderate permeability. Centimeter by centimeter, day by day, the water descends through distinct soil horizons. The O horizon at the surface is mostly organic matter, decomposing leaves and twigs. The A horizon below is the topsoil, where organic matter mixes with mineral particles. The B horizon, or subsoil, is lighter colored, with less organic matter and more mineral content, often enriched with clays that have washed down from above. As water moves through these layers, it carries dissolved substances. Organic acids from decomposing leaves dissolve slightly in the water, lowering its pH. Minerals from weathering soil particles, calcium, magnesium, potassium, sodium, dissolve in tiny amounts. The water, which fell as nearly pure H2O from the cloud, becomes a dilute mineral solution as it percolates through the soil. At about 1 meter depth, the water reaches the sea horizon, weathered bedrock, fragments of granite that are breaking down into soil. This layer is the interface between soil and solid rock, a zone where physical and chemical weathering are actively breaking solid granite into smaller and smaller pieces. The granite here is fractured. Granite, despite its hardness and durability, is not a single solid mass but is crossed by countless tiny cracks. Joints formed as the rock cooled from molten magma millions of years ago, fractures created by the stress of overlying rock being eroded away, cracks widened by the freezing and thawing of water over thousands of winter-summer cycles. The water enters these fractures, seeping through openings that range from less than a millimeter to several centimeters wide. The flow through fractured rock is different from flow through soil. In soil, water moves through networks of tiny pores between particles. In fractured rock, water moves through discrete fractures, flowing along the fracture surfaces like a thin film. The fracture walls are rough at the microscopic scale, and water molecules adhere to them, forming a thin boundary layer where flow is slower. The bulk of the flow occurs in the center of the fracture, where water can move more freely. But even here, the flow is slow, perhaps a few millimeters per day through fractures, limited by the narrow apertures and the tortuous interconnected network of cracks. The water reaches true bedrock, solid granite below the weathered zone. But even here, fractures allow water to penetrate. Granite is crystalline rock, made up of interlocking crystals of quartz, feldspar, and mica, formed as molten magma cooled slowly deep underground about 50 million years ago. The rock is hard and dense, with virtually no porosity within the crystals themselves. But the fractures that cross the rock create secondary porosity, allowing water to seep through even solid granite. Days pass as the water moves through the mountain's interior, always downward, always following gravity's gentle pull. The flow is measured in millimeters per day, sometimes less. This is groundwater now, part of the hidden reservoir of water stored in rock and soil beneath Earth's surface. Globally, groundwater represents about 30 times the volume of all lakes and rivers combined, though it moves far more slowly than surface water. The temperature is constant down here, insulated from the day-night and seasonal variations of the surface. At 1 meter depth, the soil temperature equals the average annual air temperature, perhaps 8 degrees Celsius in this mountain climate. Deeper still, the temperature increases slightly due to the geothermal gradient. Earth's interior is warmer than its surface and heat flows outward. The gradient is small, about 25 degrees Celsius per kilometer of depth in typical continental crust, but measurable. At 50 meters depth, the temperature might be 1 degree warmer than at the surface. In the darkness of the rock, in the silence of mineral and water, the groundwater waits and seeps and slowly flows. There is no light here, no photosynthesis, but there is life, bacteria that live in the rock fractures, organisms that can derive energy from chemical reactions involving minerals and dissolved oxygen, part of the deep biosphere that exists throughout Earth's crust. The journey through the mountain's interior is long. The water table, the surface below which all fractures and pores are saturated with water, slopes gently downward, roughly parallel to the mountain's surface but with a gentler gradient. Water in the saturated zone flows along this slope, always seeking lower elevations, moving through the interconnected network of fractures. Weeks pass, then months. Our droplets molecules, now mixed with other groundwater, seep through granite at a depth of perhaps 20 to 50 meters below the surface. They move perhaps 10 meters per month, a slow underground river invisible from above, following the subtle slope of the water table through the mountain's fractured interior. Eventually, after a journey of perhaps a kilometer through the mountain's depths, the water reaches a region where the fractured bedrock gives way to looser material, ancient glacial deposits of gravel and cobbles, deposited thousands of years ago when ice sheets covered this mountain. These deposits are more permeable than the solid rock, and the water flows more freely through them. The flow accelerates, not to anything a human would call fast, but faster than before. Perhaps a meter per day now instead of millimeters. And then, one spring morning, the water emerges. A small spring seeps from the mountainside, a place where the water table intersects the ground surface on a steep slope. Water bubbles up through gravel and flows over moss-covered stones, creating a tiny stream perhaps 10 centimeters wide. The water is crystal clear, filtered by its long journey through rock and soil, cold and pure. Our droplets molecules emerge with this spring water, returning to the surface after their subterranean journey. They have been underground for nearly 6 months, seeping slowly through the mountain. Now they flow once more in sunlight, part of a small mountain stream. The stream flows downslope, following the natural drainage of the mountain. It tumbles over rocks, creating tiny waterfalls a few centimeters high. The water foams white where it splashes, then settles into clear pools before flowing onward. The stream is joined by other springs, other tiny tributaries, and it grows. 10 centimeters wide becomes 20, then 50. The flow increases from a trickle to a substantial stream. The gradient is steep here on the mountain's upper slopes, and the water flows quickly, splashing and tumbling over the rocky streambed. The water is highly oxygenated from its turbulent flow, and life thrives here. Aquatic insects cling to rocks in the stream, mayfly nymphs and caddisfly larvae, adapted to the cold, fast-flowing water. Moss and algae coat the rocks, and small fish dart in the deeper pools. Our droplet flows with the stream, tumbling over rocks, swirling in eddies, sometimes trapped briefly in a quiet pool before being swept onward again. The journey is rapid compared to the slow seepage through the mountain, but still gentle by human standards, a few kilometers per hour perhaps. The stream descends the mountain, losing elevation steadily. The gradient gradually decreases as the stream reaches the mountain's lower slopes. The streambed changes from bare rock to a mixture of rock and gravel, then to gravel and sand. The banks become more defined, lined with sedges and willows. Other streams join this one, confluences where two flows merge into one larger stream. With each joining, the water volume increases and the stream grows wider. 3 meters wide, then 5, then 10. The character of the flow changes. The steep mountain gradient gives way to gentler slopes. The tumbling cascade becomes a flowing stream. The water is still clear and cold, still moving swiftly, but the violence of the mountain torrent has been replaced by a steadier, more sedate flow. The stream enters a forested valley, following the valley floor between mountain ridges. Conifers give way to mixed forest, birch and alder along the stream banks, fir and hemlock on the slopes above. The stream meanders slightly now, able to wander across the wider valley floor rather than being confined to a steep ravine. Days pass. The stream flows onward, always descending, always following gravity's pull toward the sea. Our droplets molecules travel with it, mixed with the billions of liters of water flowing in this stream. The river becomes substantial, a waterway that truly deserves the name. The transition from stream to river is gradual, not marked by any particular point, but the character of the water has fundamentally changed. The river is now 50 meters wide in most places, sometimes wider where it spreads across shallow riffles, sometimes narrower where it cuts through resistant bedrock. The depth varies from half a meter over gravel bars to 3 or 4 meters in the deeper pools. The flow is steady and powerful, hundreds of cubic meters per second, enough water to fill an Olympic swimming pool every few seconds. The river valley has changed too. Gone are the steep V-shaped valleys of the mountains, carved by the down-cutting action of fast-flowing water. Here, the valley is wider and U-shaped, a profile created by glaciers during the ice ages. 20,000 years ago, this valley was filled with ice, a river of frozen water hundreds of meters thick, grinding slowly down valley, scouring the bedrock beneath, creating the broad, flat valley floor that the river now occupies. That valley floor is made of glacial till and outwash, deposits left by the ice and its meltwater. Beneath the current river channel lies a deep layer of sediment, gravel, sand, silt, deposited over thousands of years. The river cuts down through this sediment, creating a channel, but the sediment is so thick that the river has never reached bedrock here. If you could drill down through the riverbed, you would pass through tens of meters of layered sediment before hitting solid rock. The river meanders across this floodplain, creating sweeping curves called meanders. The path of the river is not straight but sinuous, snaking back and forth across the valley floor. These meanders form because of the way water flows in a channel. In a straight channel, slight irregularities create zones of faster and slower flow. Faster water on one side erodes the bank, while slower water on the other side deposits sediment. This creates a bend. Once a bend forms, the physics of flowing water exaggerates it. The fastest current swings to the outside of the bend, eroding that bank, while the slowest water is on the inside, depositing sediment. The bend grows, creating a meander loop. Over time, meanders migrate across the floodplain. The outside of each bend erodes, cutting into the valley floor, while the inside deposits sediment, building up a point bar. Some meanders grow so pronounced that they nearly meet themselves, and eventually the river cuts across the narrow neck of land, abandoning the old meander loop and creating an oxbow lake, a crescent-shaped body of water cut off from the main channel. Our droplet flows with the main channel, carried by currents that vary in speed and direction depending on position in the river. The fastest water is in the center of the channel, near the surface. Here, water is farthest from the friction of the riverbed and banks, and it flows at perhaps 2 to 3 meters per second. Near the banks, and especially near the bottom, friction slows the water to perhaps 1 meter per second or less. The flow is turbulent, not laminar. Turbulent flow is characterized by chaotic motion, with eddies and swirls on all scales, from millimeters to meters. A droplet does not simply move downstream in a straight line but follows a complex, wandering path, sometimes moving faster, sometimes slower, sometimes even backward in a local eddy before being swept downstream again. The river carries more than just water. Suspended in the flow are particles of sediment, clay, silt, fine sand. This suspended load gives the river a slightly turbid appearance, a faint cloudiness that distinguishes it from the crystal-clear mountain streams above. The amount of sediment depends on the river's velocity and the availability of erodible material. During floods, the sediment concentration increases dramatically, and the river can become brown with suspended soil. But today, in moderate flow conditions, the suspended sediment is modest, perhaps 100 milligrams per liter, enough to give the water a slight haze but not enough to be called muddy. There is also a bed load, larger particles that roll and bounce along the riverbed, too heavy to be suspended but light enough to be moved by the current. Pebbles and small cobbles tumble downstream during high flows, gradually working their way down valley, becoming more rounded with each kilometer as collisions knock off their sharp edges. The grinding of these stones on the riverbed creates a subtle rumbling sound that can sometimes be heard above the river's rush. The river's ecosystem is rich and complex. In the water column itself, phytoplankton drift, microscopic algae that photosynthesize using sunlight that penetrates the clear water. Zooplankton graze on the phytoplankton, tiny crustaceans and other microscopic animals, barely visible to the naked eye. Small fish feed on the zooplankton, and larger fish feed on the smaller fish, creating an aquatic food web. The riverbed supports its own community. Aquatic insects cling to rocks, mayfly nymphs with their distinctive three-tailed appearance, caddisfly larvae in their portable cases made of pebbles or plant matter, stonefly nymphs hunting smaller insects. These insects are adapted to the flowing water, with streamlined bodies and grasping claws to hold onto rocks in the current. They feed on algae growing on the rocks, on organic matter drifting downstream on each other. Fish are abundant. Salmon and steelhead sea-run trout migrate up this river each year to spawn, though they are not present right now, this not being their season. Resident trout live here year-round, cutthroat and rainbow trout hiding in the deeper pools, darting out to snatch insects drifting by. Sculpins, small bottom-dwelling fish with large heads and mottled coloration, rest on the gravel bed, camouflaged against the stones. Along the banks, the vegetation is lush. This is a riparian zone, the interface between aquatic and terrestrial ecosystems. Willows and alders grow with their roots in the water, stabilizing the banks. Cottonwoods tower above, their roots extending deep into the sediment to reach the water table. Devil's Club and salmonberry create dense thickets. The vegetation provides shade, cooling the river water, crucial for fish that are sensitive to temperature. It also provides organic matter, leaves and twigs that fall into the water, beginning a new cycle as they are broken down by bacteria and fungi and consumed by aquatic insects. Beavers have been active along this stretch of river. Several dams are visible on side channels and smaller tributaries. Intricate constructions of logs, branches, and mud that create ponds behind them. These beaver ponds slow water flow, trap sediment, provide habitat for a different set of organisms than the flowing river itself. The main river channel is too large and too powerful for beavers to dam. The flow would wash away any dam they could build, but they thrive on the smaller channels. Our droplet flows through this ecosystem, part of the water that sustains it all. The molecules that began in the deep Pacific, that fell as rain on the mountain, that percolated through granite and emerged at a spring, that have flowed downstream for days. These molecules are now passing through this temperate rainforest river, carrying dissolved minerals and oxygen at exactly the right temperature to support cold water fish, moving at exactly the right speed to transport sediment without causing excessive erosion. The river continues its patient journey toward the sea, losing elevation gradually. The valley widens further as the river approaches the lowlands. The gradient decreases steadily, from perhaps 2 meters per kilometer in the upper valley to 1 meter per kilometer here, and soon to be even less as the river reaches the coastal plain. This decreasing gradient means slower flow, which means less erosive power, which means the river begins to deposit more sediment than it erodes. The river's size continues to increase as tributaries join it. Each confluence brings more water, creating a larger river downstream. With each joining, the river's discharge increases, the volume of water passing a given point per unit time. Discharge is measured in cubic meters per second, and this river, having collected water from hundreds of square kilometers of watershed, now carries perhaps 500 cubic meters per second in normal flow conditions. During spring snowmelt or after major storms, the discharge can increase to thousands of cubic meters per second, causing floods that overtop the banks and spread across the floodplain. The river continues its inexorable journey toward the sea. The mountains fall behind. The valley widens further. The gradient decreases until it is almost imperceptible, a drop of perhaps 1 meter per kilometer now, compared to the hundreds of meters per kilometer on the steep mountain slopes. The river slows. The flow is still substantial, still moving downstream, but the sense of urgency is gone. The water meanders lazily across a wide coastal plain, creating broad loops. The riverbed is now mostly silt and sand, fine particles carried from the mountains and deposited here where the current is too gentle to carry them further. The water is no longer crystal clear. It carries suspended sediment, clay particles, organic matter, the accumulated nutrients of the landscape it has drained. The water is slightly turbid, slightly cloudy, though not dirty. This is the natural state of a mature lowland river, carrying the products of erosion and biological activity from its entire watershed. Our droplets molecules flow with this slower current. Days pass in peaceful downstream drift. The riverbanks are lined with willows and cottonwoods. Marshes and wetlands occupy low areas, and the river branches into multiple channels and places, creating a complex network of flowing water. And then, gradually, the river widens further. The banks become more distant from each other. The flow spreads across a broader channel. Tides begin to make themselves felt. The subtle rise and fall of water level as the ocean's tidal bulge, created by the moon's gravitational pull, reaches up into the river's mouth. This is the river delta, the final transition zone between river and sea. The river's current, already slow, becomes slower still as it fights the incoming tide. The water spreads across tidal flats, wide expanses of mud and sand that are covered at high tide and exposed at low. Salt marsh grasses grow at the edges, plants adapted to this daily inundation by brackish water. The fresh water from the river meets salt water from the ocean. At first, the waters do not mix easily. Fresh water, being less dense than salt water, tends to flow over the top of the incoming tide, creating a layered system with fresh water above and salt water below. But wind and waves and tidal currents create turbulence, and gradually the two waters mix. Our droplets molecules are in the surface layer, part of the fresh water flowing outward. But as the delta broadens and the mixing intensifies, they are gradually diluted with salt water, the chemistry of their surroundings changing from fresh to brackish to nearly fully saline. The delta opens into a broad estuary, and beyond that, the open ocean. The river's current carries the water outward into this larger body. The boundaries dissolve. Where does the river end and the ocean begin? There is no clear line, only a gradual transition, a zone where river and sea merge. The water flows past the last of the river's deltas, past the final mudflats and marshes. The bottom drops away. The water deepens. The confinement of the river channel is gone, replaced by the vastness of the sea. Our droplet is in the ocean again. Not the same ocean where this journey began, that was the Pacific, and this is a different sea entirely, but ocean nonetheless. Salt water surrounds the droplet's molecules now, the familiar taste of dissolved minerals, the density and pressure of seawater. The transition from fresh to salt has been gradual, but it is now complete. The molecules are part of the ocean's surface layer, floating in the upper meters where sunlight penetrates, where waves create motion, where the water is warmest. For a time, the water circles in the coastal zone. Ocean currents along the coast carry it southward, mixing it with other coastal waters. The molecules drift in this boundary region between land and open sea, sometimes moving offshore, sometimes returning toward the coast. But gradually, over days and weeks, they are carried further from shore. Wind-driven currents push the surface water outward. The water moves into the open ocean, away from the coastal influence, into the realm of deep blue water. The molecules drift in the surface current, part of a great gyre, a circular current system driven by wind patterns. They move with this current, covering kilometers per day, slowly spiraling across the ocean basin. Time passes, weeks, months. The water is warm in this surface layer, heated by the sun. Sometimes it cools at night, sometimes it is churned by storms, but overall it remains in the upper ocean, part of the wind-mixed layer. Then, as autumn approaches and the weather changes, a storm passes over this region of ocean. Strong winds churn the surface, driving waves and mixing the water downward. The surface layer deepens as warm water is mixed with cooler water from below. Our droplets' molecules are caught in this mixing. They are pushed downward, out of the sunlit surface layer into deeper water. The temperature decreases. The light fades. Pressure increases. The molecules sink further. They are part of a complex three-dimensional circulation now, surface water being subducted, pushed down by converging currents and density differences. This is the beginning of the thermohaline circulation once more, the great overturning of the ocean. The water sinks to 100 meters depth, then 200, then 500. It is moving into the ocean's interior, leaving the surface layer behind. The descent continues, steady and slow. 1,000 meters, 2,000. The water is cold again, the pressure immense, the light gone. The molecules are returning to the deep ocean, to the realm of slow currents and patient time. At 3,000 meters depth, the sinking slows. The water has reached a layer of neutral buoyancy, where its density matches the surrounding water. It begins to flow horizontally now, spreading out along this depth layer, part of a deep current moving across the ocean basin. The current is slow, centimeters per second perhaps, but persistent. Day after day, month after month, it flows. Our droplets' molecules drift with it, back into the deep ocean's embrace. Years will pass before they rise to the surface again. Decades, perhaps. They will flow through the ocean's depths, part of the great overturning circulation that takes centuries to complete. They will drift past underwater mountain ranges, through deep ocean basins, along the contours of the seafloor. Eventually, after a journey longer than human lifetimes, they will rise again. They will return to the surface in some distant part of the ocean, warm in the sun's light, and evaporate once more. They will join the atmosphere, condense into clouds, fall as rain. The cycle will continue, endless and patient, the same cycle that has turned for billions of years and will continue for billions more, water moving between ocean and sky and land, driven by the sun's energy and Earth's gravity, an eternal circulation that sustains all life on this blue planet. The droplet rests in darkness once more, deep in the ocean, part of the slow currents that flow through the abyss. Its journey has come full circle, from ocean to sky to mountain to river and back to ocean. Yet it is also just beginning again. For water, there is no true beginning and no final end, only the endless turning of the cycle. In the quiet depths, the droplet waits. The current carries it slowly onward. Somewhere above, separated by kilometers of water, the sun shines on the surface. Waves rise and fall. Rain falls on distant lands. Rivers flow to the sea. And in time, when the patient centuries have passed, the droplet will rise again toward the light, ready to begin another chapter of its eternal tale. The story continues as it always has, as it always will, the ancient dance of water on earth.